Thanks, Jocelyn, and thanks for making, just increase the pressure level expectations there. So, thanks, folks. It's a pleasure to be here speaking today. I've had the pleasure of talking at many AusNOGs in the past, actually. I think this is my fourth one, but there would be, I suspect, like a 10-year hiatus between those. So that might be showing my age a little bit. Today, I'm going to talk about AWS and our journey to running on our own equipment. This has kind of been a journey for us. It's kind of cool. It's something we've actually done over the last 3 years, and kind of the best thing about it is no one really realized, right? We fundamentally changed the network, and very few people realized it, right? Touch wood, we didn't have any significant problems or outages. When we, at AWS, when we talk about the network and what we do and how we do it, we actually have a fairly standard slide deck that we have called No Packet Left Behind. And kind of besides sort of the humor in that title, I guess, it is kind of how we approach things. We're never happy when we do have packet loss or any availability drop. We always do go and look at that, root cause it, figure it out, and make sure it never happens again. And it's sort of that relentless continual iteration on that is kind of the basis for what we do in terms of networking and how that works. But it's also, it's sort of part and parcel of why we did what we've done. We used to have a large global network running on vendor gear. At this point, we don't, right? We've swapped it out to run on our own. The reasons around that is actually primarily around availability. We just weren't happy with the status quo of where things were. We didn't see a path to dramatically making it better, except by owning it ourselves, and that's kind of what we've been doing. So, if I sort of look at what the talk today is about, I'll talk a little bit about our global infrastructure, what that looks like, our journey, how we've been reinventing our network, and what that looks like from a hardware, software, controllers, systems, tools perspective. The actual network architecture itself, what it actually looks like, what even the devices look like, and I've got some pictures of some of our networking devices. For after the talk, during one of the breaks, we've actually got one off on the side table over there with its lid off if you want to see it. It's not very interesting, it's just a sea of heat sinks, but it's kind of cool if you do want to see it. I'll talk a little bit more about how we automate things within our network as well. So, to get started with this, we'll start with a map of the world. This is our stylized version of the world in these tiles. Not very interesting, right? But if we layer things on top of that, we would start with what we call our regions, and we've got a number of regions around the world, and within each region we have a number of availability zones. When this slide was created, there was 31 regions available and 99 availability zones. The number is actually perpetually wrong. So I think since this date, I think 2 of the regions have come up, and I think we've announced 2 more or something like that. It's just always, keeping this up to date is a challenge, right? But it's extensive, right? We have these regions around the world, and for us, like, these are pretty big footprints of data centers, right? We use a number of facilities. Often it's our own, and these are massive, massive construction projects in their own right. We can also look at this in terms of local zones, and for us, local zones is where we put compute, storage, network closer to where the eyeballs are. And local zones, these started initially in North America with, there was a desire for Dish as a 5G provider in the US to run their network on AWS. We put compute in closer, so sub-millisecond from wherever the 5G terminates the antennas. And we've kind of extended this out as time has gone by. This has actually been one of the benefits we've had of commoditizing our network or building it on our own. Historically, from a network design standpoint, we used to have different things inside the network, inside an availability zone or a data center, separate from what we called a transit center, where we would connect to you guys, and separate from what we had as an edge site. Kind of part of this journey is we made it actually the same thing, so we could land anything in any location with no restrictions whatsoever. So anywhere where we are doing peering, or anywhere where we're connecting to others, or we've added CloudFront for CDN or something, we can land a local zone there now as well. And in fact, we've done that. This shows coming soon as Perth and Brisbane. I think Perth, again, this map is wrong, right? Perth is live, Auckland is live. In New Zealand. I think Brisbane is the dot there that is almost live, I think. So But again, this is perpetually wrong or out of date. Edge locations, we have lots more of those. We have lots of places where we do direct connect, and that's our direct connection into enterprise customers who want private connections into us. CloudFront's where we do our CDN and where we do Route 53 as well, so where we do DNS as a service. We list this as being 450 plus CloudFront POPs. In fact, this number is probably wrong. It's more like 600 at this point. I think in the last 18 months, we've deployed more CloudFront than we have in the entire history of CloudFront. And again, this is sort of part and parcel of kind of how we've had to do things to deal with the demand, but also the flexibility that we've had in terms of the network. We layer all these things on top. We start to get lots and lots of dots that are covering lots and lots of places. And what's missing here is the actual network to tie it together. And this is kind of what our backbone, global backbone looks like, right? So it does span the globe. We have an awful lot of capacity in an awful lot of places. Again, this map is completely wrong at this point, right? We do actually have connectivity to Brisbane, which doesn't show there. But if we went back 6 months, that probably wasn't there. So that's the kinds of things that we're just perpetually, continually doing, but keeping the slides up to date is the hard part. This is kind of the steady state for us, right? We're adding so much capacity in so many places all the time that we had to reinvent ways of how the network works because it simply wasn't scaling what we were doing. We had an IGP. Actually, Jeff mentioned earlier, like, why not just use ISIS? We had ISIS. We had an ISIS network that was 3 times larger than the next largest, according to various vendors. We know intimately the challenges with scaling that and where they break, right? And in some cases, like, we had to evolve this network to a point where we don't use an IGP anymore. We don't have a global IGP. And again, this is about availability and reducing the blast radius of things. So we've had to kind of reinvent some protocol things along the way as we've done that. And there's super cool things that we've done in terms of enabling those things along the way, right? So. Gaurav kind of talked a little bit about Thursday Night Football, but for us, this was a great opportunity for us. We started out on this journey 3 years ago to reinvent the network, and we were actually starting from, we know that we'll need to support these live streaming events, and they create these huge demands in traffic. There are some various numbers thrown around, but yeah, we had to scale internet capacity in North America in a series of locations by more than 100 terabits to support this. And we had to do that in 9 months. In fact, Thursday Night Football got brought forward a year. We thought we had 2 years to do it, and it turned out we had 9 months to do it. So it's a testament to, like, some of the very talented people that I represent by standing up here talking. But we can just land huge amounts of capacity, and stuff just works, right? Amazon, I think, having the rights to Thursday Night Football, I think every Thursday night it was costing Amazon, I think, $14 million, whether we were successful at streaming it or not. So there was a lot of incentive to, like, make it work the first time, right? And we didn't know where the traffic was going to be exactly. We had models. We worked very closely with ISPs to connect deep into their networks, but it wasn't until match day that we actually saw if that hard work paid off or if there was more work to do. I'm happy to say it did actually work, but for someone who doesn't follow American football, I watched an awful lot of football every Thursday. So, okay, so what does this mean in terms of how we've been sort of reinventing our network? And for us, it's a few different things. So for us, we are at the point now where we have a network that runs entirely on our own hardware and entirely on our own software. And it's the complete end-to-end. And by the complete end-to-end, we don't use anyone else's tools for doing configuration or telemetry or NetFlow or log monitoring or alarming or insert the whole 9 yards of all the tooling ecosystem and config generation and the rest. We own all of that ourselves. So we're kind of at a size and a scope where we can do this. We're at well north of 1 million network devices at this point, and it's sort of that kind of scale that has enabled us to do it. You know, you might look at, say, a commodity device and go, is it worthwhile building your own or building your own software? At this kind of scale, yeah, it is. But it comes back to still what the business was asking for, and we were looking to make the network more available than it could otherwise be or otherwise previously was, right? So the key here was we started out with literally a clean sheet of paper, deciding what it was that we viewed utopia as, what do we want the network to look like as, and then we just worked backwards from that. And kind of what was kind of key in some of this is it really comes down to simplicity scales. It's very easy in the network world to turn on one more feature, to do one more thing. And this was particularly true as the network gets larger, convergence gets slower, maybe you find those nerd knobs that can speed things up, you turn those on, or maybe there's a new feature or a new RFC, you turn those on, things are better, right? But you've probably also introduced more complexity in that as well, and more opportunity for bugs as well. So one of the things that we did here was actually in our network devices, we probably used 10 features, and that's it. We use the absolute bare minimum, and we think really, really deeply before we turn any new feature on. And the key there is simplicity scales, right? We're always focusing on the benefits, right? It's nice to build your own network devices, great. But actually that's just the only reason we actually do this is we want to deliver our customers packets. We get paid when we deliver packets. We don't get paid when we don't, right? Some of the magic of the cloud is that it's infinite compute, it's infinite storage, it's infinite network, and it just works. And if the network isn't working, then there is no cloud, right? So this is sort of something that we work really, really hard to do. But by having that clean slate, right, we were free to examine the trade-offs of how to do things, right? And it really did become an exercise in simplicity of kind of not doing things. The list of things that we didn't do is extensive compared to the list of things that we have actually done. So if we kind of dive into this a bit, this is a 12.8T switch. Actually, it's clearly not a 12.8T switch. It's a PowerPoint picture of a box, right? So the device in question is, this is kind of what it looks like. And this is one of the green ones we actually have over there that you're free to look at any time. It's not actually that interesting to look at. It's just a sea of heat sinks, right? And what's under the ginormous heatsink is a 12.8T system on chip. And that's it. It's a commodity thing. We actually don't build that thing. We source that from multiple people who can provide that. And you can probably guess who they are, right? It's not, that's not really hidden who that is. But this is actually the same kind of device that you might put inside a data center as a top-of-rack switch. Maybe you don't have a 12.8T top-of-rack switch, but it's the same class of family of that device. We actually have devices at this point up to 51.2T, right? You can get a 51.2 terabit system on chip. We don't yet use that because it's not yet cost effective to use it. This is the most cost effective thing that we have. So this is the building block. But nothing precludes or prevents us using a 25.6, 51.2. This just happens to be the current sweet spot for doing it. The picture on the top right is the CPU complex, and it's a little bit hard to see in this picture, but if you saw it on the real device, you'll see what I mean. This is actually the equivalent of the NIC that we put inside our servers inside AWS. So we have something that we call Nitro or dongle, and it's normally a smart NIC of where we run the virtual networking stack of EC2 and run the storage. It's actually the same control plane that we use on this device as well. And you can kind of see how ghetto it is because it's a PCIe card and it has some transceiver cages on the one that we have here that are still there present even though they're not actually plugged into anything. Like there's an RJ45 for IPMI and there's a QSFP transceiver cage that you can't plug anything into, but it's actually just because it is the same NIC that we use, right? So we do make use of our own CPUs in terms of doing this, and we do things in terms of then how we secure it and things like that. But other than that, this is just kind of a common all-garden 12.8T thing. When we actually provision capacity on these things, we deploy them as a rack, right? This is the basic building block of capacity that we deploy. We stick 32 of these in a rack, and we call that 100T of capacity. For those of you that are really, really good at doing math in 12.8T increments, you go, that's not 100T, it's actually 400T, and you're quite right. What we've actually deployed here is something that starts out life as a 2-tier clos fabric, but it can grow up to be a 3-tier clos. So this is our building block of we can deploy 100T of usable capacity. It's actually got another 100T northbound from it to the second tier of a clo fabric, and then that in itself has ports that are left over for connecting the third tier of a clo as well. And that's kind of how we build capacity, and that's how we kind of scale it out. So if we were to see this as a picture, these switches are blue. These are a different one than the green one over there. We've got some red ones, we've got some purple ones. There is a bit of a history there of, I thought it was kind of cool, just as an aside, but it turns out it's completely wrong. We had blue ones, and then we had green ones, and then we somewhere along the way we had ones that were painted red. The sheet metal was red, and they could do encryption built in. And I thought, okay, right, red maybe for a firewall or something. And then we got to the point where we integrated the encryption in the same things as well, and they became purple ones. And I was going, okay, maybe it's if you get green and red and combine them together, you get purple, but then I'm going, that doesn't work in the color chart. That's the wrong color. It would be like this murky brown or something. Anyway, I thought it was some cool thing that someone was doing color coding. Anyway, it just turns out that actually, when I asked the question, the hardware engineer just went, oh, we just chose the Pantone color of the year as our color. And it was something way, way more basic than that, which was very sad. I much preferred my logic of take a red one, take a green one, combine them. These were the blue ones, but yeah, we've evolved from that to the green ones, and they're just representing different devices built essentially in different years, right? So we can start with this rack, and we can scale it out horizontally, right? And we can scale up to 32 racks wide, which is 3.2 petabits per second, right? At that point, we would call this a fabric, and it doesn't mean that we can't drop more than one fabric in a location. It's an awful lot of capacity to fail at this point, right? So we probably wouldn't actually grow this thing to 3.2 petabits, but we could if we wanted to, right? It allows us. One of the challenges with doing this, we're big believers in these simple devices, right? Single system on chip, single thing to fail, not multi-chip, not line cards, not modular devices. But it means that you end up with a lot of passive copper cables to connect these things together, right? These are cheap, or relatively inexpensive, let's say. But the challenge is actually cabling these things, right? As speeds and feeds have gone up, these are 400 gig DACs here, and it's getting really hard to cable these things up, right? I kind of feel sorry for anyone trying to remove one of these devices from the rack and trying to get all these cables back in, right? So one of the things that we've been doing here is we've actually innovated, I guess, on some of the even just simple things like DAC cables. We have a combination of passive DAC, where they're larger diameter cables, and then we have active DAC cables where they're smaller diameter because we have a retimer in the transceiver. This is also where we have the opportunity to sort of think different. As we're manufacturing our own devices, we've been very certain about what ports we're using for building using the passive DAC copper cables, and we can ensure that they are the best trace length on the PCB in terms of the best signal integrity available. And that then results in we can build this thing cheaper because we don't need to put in active components. So we actually have multiple variations of things of how we do this, right? This is one of the different variations of devices. This one here is targeted at actually doing long haul. We can do 400 gig ZR in this, so we can do DWDM transceivers straight into it. We have MACsec encryption on these ports. Because we were supporting super high power transceivers, we're supporting up to 27 watt transceivers in this thing. We couldn't build it in 1U. We needed more space for doing cooling. So we kind of did this hybrid design of this one. This device is actually the purple one. For whatever reason, these rack, we must have run out of the purple paint. We don't have the purple paint on these ones, but that's okay. We still use it, we still ship it, right? And kind of what this is showing as well is in one of the racks that we have, you know, in this case, we don't have traditional power supplies in this. This is a custom rack that we have where the rack itself, we have centralized power supplies, and that's what we have in the middle here. We actually have batteries here as well, so we don't have UPS centrally. We actually do it per rack, and in fact, it's distributed to just the devices where we care about it, right? So we can do some really, really interesting things there. Historically, if we looked at things like cabling, right, you can kind of see the picture on the right is, you know, a rack that some poor person is trying to cable up, and it's just a mess of single mode fiber that they were putting together, right? And in fact, we'd burn a rack position next to these things to put in a patch panel, right? So an unused rack position for doing that. Now, at 10 gig, 40 gig, you could do breakouts, right? So you could use things like transceivers where you didn't need the patch panel because you could just build a transceiver that had the breakout for you, and then maybe you didn't need the patch panel. That was all okay, but it kind of breaks down at 400 gig, and it's less easy to do. One of the things that we did along the way is we worked with a vendor, and the vendor here was Senko in Japan, and we invented a new kind of connector called the SN connector. Now, this requires that you've got really, really small fingers, or that you, there is actually a tool that makes it easy, but you could get the breakout straight in the transceiver, right? So rather than using an MPO8, MPO12 type cable to a 4x LC or something, more connectors, more things to fail, more cost, we instead just put the breakouts in the transceiver, and you know, we deploy lots of these. We did this for our own reasons, right? I think we funded a lot of the development of this, but we didn't, it's not proprietary to us. Like, anyone can buy this, right? These optics exist in the open market, right? So if we look at things, you know, again, back to our rack, right? We have just a small number of variations in things that we build, and we cookie cutter things out in a fairly consistent way. But it's kind of, you know, we roll the rack into location, we plug up its power, we cable up the things that we need to. It's actually come from our manufacturing line or our integrator pre-cabled in the rack. So we just move racks around the place to a location and then power it up. And then when it powers up, it just pixie boots, right? So it does ZTP. We'll check that nothing got tampered with along the way. We can do secure boot and various things from a security standpoint. And you know, it just powers up, right? With the latest and greatest config, it knows where it is in the network and just self-configures to whatever, right? So seems fairly straightforward, but you know, there's a lot of magic and devil in the details of how that happens, right? So if we actually look at the network architecture and sort of how this fits together, right? And I think this is a picture. I just used a picture that someone else had at reInvent, but I think this is James Hamilton conducting the choir, and I think it's pretty accurate. If those of you know who James Hamilton is, he's our esteemed, I actually don't know what his title is, but anyway. James sort of had a vision of how we could commoditize the network, and sort of for the better part of a decade, AWS has had that inside the data center, and then over the last 3 years, we've been doing the same for everything outside the data center as well. The key, essentially, to this is we actually automate everything. We remove humans out of the process as much as possible. We also own our own destiny in terms of all of the tools and the systems and how we deploy things. I looked at some numbers last week, and I think we're at the point where we deploy about 2.3 million config changes a day to the AWS network. Every one of those changes has pre-checks, post-checks, validation, there's automatic rollback if something happens. We don't need humans involved in doing these things. Likewise, most of the actions where we need to remediate something, maybe there's a fiber break or a link with errors or a transceiver's failing, these are also automated actions as well. We might still need like a human to go change a transceiver if it's failing or something like that. But you know, the machine can cut tickets to humans to go do things, and again, we can kind of make it so that the people are most efficient in terms of how to go about doing that inside a data center, that they're not just doing one-offs, maybe they're doing it all in a common run, right? So I quite liked, Gaurav had a lovely picture of a NOC for Prime Video. Actually, we don't have a NOC in the network at all, so sadly. There's no fancy looking room we can point a picture of. It's just people in front of their laptops doing stuff where the automation doesn't do the job. In fact, the role of most network engineers that we have within AWS isn't to actually make operational changes to the network. It's to make changes to the automated tooling that makes changes to the network. And so it's very different. We're not logging on devices to make changes. We just it doesn't scale, and the blast radius is all wrong for doing that, right? So it kind of works the opposite way around, that we still highly value our network engineers and their skills, but they're doing something slightly different in terms of non-traditional in how they're doing it. We do have a picture of sort of what our networks look like. This is just a two-tier clause, right? There's nothing fancy there. We actually have this in a blog post that we made earlier on this year. The picture is actually deliberetely wrong in a few places, and that's just to, I use that for an interview question at the moment to get people to tell me what's wrong about this picture, but there's a couple of deliberate mistakes in there. We do actually call this the final cat, and the history of that was that all the various networks that we had inside AWS were all named after cats, and one of the very first networking people at Amazon, he's a big cat fan, has a lot of cats, and so we name things after cats, but this is the final cat. There are no more cats. So sorry to Tom Scholl, who likes his cats, but there are no more cats. It's not to say that we won't iterate this, but there'll probably be Final Cat V2, V3, smaller ones, bigger ones, whatever, right? So, just a little bit more about how we do it. Here's the purple switch, right, that I wish was, you know, red plus green, but it's just not, right? That's kind of what it looks like. A 400 gig ZR transceiver. It's not very interesting to look at, right? It's a QSFP 56DD transceiver. Woohoo, right? It's got a heatsink on it. Great. That's it, right? But we can run direct out of this device. We would use the rightmost ports for connecting into the rest of the Clove fabric, but we could use the leftmost ports for up to 6.4T of capacity. And this is typically what we would do inside a metro location if we were multiple locations in the same metro. We can technically run this thing up to DWDM up to 1,200 kilometers. It derates the longer distance you go, but there are fairly dramatic cost savings in terms of how you can do this, and quite a simplification as well in terms of the network. You're not building L1 and L3 separately from an optical standpoint. If we look at sort of how what actually runs on the network devices themselves, right? We have it sort of doesn't look that dramatically different from any vendor's network device. If you ask them, hey, what does it look like under the covers from a software standpoint? There'll be a picture of like a network ASIC at the bottom, which is probably on a PCI bus. You talk to that thing using a vendor-supplied SDK for programming it or talking to it. It's probably running Linux at this point. You know, I think the last holdout was Juniper, and Evo is Linux these days as well. And then you have various things running on top of that, right? You might have some routing protocols. You might have some telemetry. You might have, you know, management, SNMP, whatever, right? Doesn't really kind of matter. And for us, it's kind of the same thing, right? There's actually nothing special about this. And that is, again, it gets back to that simplicity, right? Simplicity scales, and we turn on less than 10 features on this device. About the only thing that we do that is special is we've innovated in doing a few things with protocols where we wanted to do better. We didn't want to implement BFD, so we actually enhanced LACP fast to go faster. We made LACP fast detect some failure cases faster than what it otherwise would. It can take up to 6 seconds for some LACP fast things, and we made that sub-second. We did some tricks inside the actual devices themselves. We just run standard routing protocols. We run everything on BGP inside the fabric and outside the fabric. But inside we're using eBGP confed. Now, the standard doesn't allow you to intermix eBGP confed with non-confed. There's sort of a quirk of we couldn't run our own AS and actually have it work. So we had to do like the 4-line code change to allow that to happen in BGP. It's kind of like, this is kind of where we're at. That we'll just do the simplest thing possible. We don't mind doing kind of scrappy things to make things work where the standard didn't work for us. But we don't deviate significantly from anything standard-wise in what we do or how we do it. So, if we kind of look at this, right, and this is a trace route from my home broadband in Melbourne, Australia, to a CloudFront server, and it's not very interesting, right? You can just do trace route to, in this case, it was Amazon.com, and no surprise, it ends up on a CloudFront server, our own CDN. Yeah, that's not really rocket science, right, that we do that. What is interesting about this, or what I'm trying to show, is it's really disappointing, right, that you can't see all these hops with stars, right? There's a whole bunch of hops that you don't get a response from. Well, the question is why? Why can't you see them? Well, various people figured it out along the way. This was a tweet from a few years ago where someone was doing a trace route across public IPs inside Amazon and going, hey, there's Class E addresses in there. What's up with that? And we even had Ripe go and write a blog article on how they think we're using Class E. And we even had a Reddit thread and Hacker News as well. So we know that we've hit peak geek when people are, there's hundreds of comments trying to figure out what it is that we're doing. In practice, it's very, very basic what we were doing here. We use a lot of IP addresses for network infrastructure. You know, we have more than 1 million network devices. We don't want to give every one of them a public IP. We've run out of every piece of private address space available. Doesn't matter where, right? 10/8, 172.16, 164. So where do we go? What do we do? Now, the answer could be maybe we make it v6 only for our stuff, but how do you answer a v4 trace route? And the answer is you can't, right? So what we did was we use Class E. So we have lots and lots of devices in Class E. This doesn't really hurt anything. I mean, I can show you like another trace route of this is from an EC2 instance in Melbourne to an EC2 instance in Sydney. The trace route itself doesn't matter. We've got some hops that were some public IPs, but the majority of hops are Class E. Anytime you get Class E, you're on the new network. Is kind of one of the giveaways, but in fact, you're not even seeing all of the devices here because we don't do TTL deprecation on some things as well. It's hidden from you. The network is so big that we exceed 64 TTL hops in a bunch of places. So, and that just breaks a bunch of OSs that have a default of 64 TTL. So we've had to be TTL pruning along the way as well. Now, it's these Class C addresses and sometimes the 164 ones that we used. Those are the reasons why traceroute from the internet shows up as stars. We will actually change this, right? This is one of the beautiful things about owning our own thing. We can change it to be whatever it is that we want. So what we're going to do is we'll make it actually respond back from an anycast address. It'll probably be from something like 3.4.5.6 or 3210 or some memorable address that we happen to own. And we'll put some fancy reverse DNS on there that means something. But we'll probably embed something in that packet that at least gives you a way of identifying that it's not a packet looping on the same IP, that they are actually different. Right? We might embed an MPLS label or something in there to disambiguate that, yes, the packet is actually making forward progress. But again, these are kind of like first world problems that we have of there's just too many devices, right? And public IPs are expensive, and it would be, you know, we would have burnt through about $1 billion worth of IP address spaces if we were numbering these out of public at this point. So, yeah, that's not a good use of money, let's say, right? If we actually look at how we actually do the peering on this, so one of the things that I haven't really talked about was when we built this thing, we replaced every layer of the network of what we previously had, and historically we had 7 layers of the network was the typical place where different things doing different things. So we might have had routers that were facing internet peers, maybe some of you guys. We might have had backbone routers that were LERs, backbone routers that were LSRs, and yeah, aggregation routers and all these different layers doing different things. When we turn this into a single fabric, one of the goals that we wanted to do was make it easy from a capacity deployment standpoint. We didn't want different things for different uses. We just wanted to deploy a common thing. And in fact, what we've done here is we can actually attach internet peers onto the same devices alongside other things. So we could have a device that has an internet peer on port 1, maybe we've got EC2 attached on port 2, maybe it's S3 attached on port 3, CloudFront on port 4, Route 53, port 5, whatever. Doesn't, maybe a backbone link, port 6. But we want to be able to basically just fill up all the ports of a device and then move on to the next device, and fill up all the ports and move on to the next one. In fact, we want to actually connect things, if we can, ideally minimum of 4-way redundant. We just like that as a pattern, because then you can have one thing fail and you're at 75% of the capacity, and it's not necessarily urgent to go remediate that straight away. You know, that's nice if we can do that. But we wanted to make it easy from a deployment standpoint, and this was kind of crucial for us during COVID. We couldn't get people into facilities with any reasonable time frame. We had to limit who could go in, and you know, the striping of, you know, physical, how many people can physically visit a facility at a given point in time. And a big part of this was then, how do we enable deploying capacity in the easiest possible way, where we have to do, you know, literally the least number of truck rolls is maybe how you might describe it. And so for us, collapsing all the layers of the network made a lot of sense in terms of how we do that. One of the things that we do here, though, is we do have a common device that we are deploying like literally everywhere in the network. So what is the top of rack switch inside EC2 is the same device as what it is as a core router, or what it is internet peering wise. But you know, it'd be really, really hard to fit like multiple full BGP feeds worth of peers into the amount of RAM this device has. So one of the things that we actually had to do was, for internet peering, we moved it off the device itself. So you can peer with us. It shows up just the same as any other BGP session does. Looks just the same. You can do TTL1 to us, it works. You can do TTL255 to us, it still works. But in fact, what you're peering with is not actually on the device itself. It's in a container on some compute somewhere nearby. Probably in the same location, but it actually technically doesn't have to be, right? We put BGP packets into a tunnel, and off they go to where we run the control plane for that. Our reasons for this were kind of pragmatic, right? We didn't want to put more RAM in these devices. They come with 8 gig of RAM. We didn't want to put 16 or 32 or something, right? We didn't want to create a snowflake. But it also provided an opportunity for like, hey, can we do better with internet peering? Can we do more fancy things in terms of, let's say, how we iterate software? And we can upgrade, let's say, the BGP stack that we use for internet peering on a per peer basis if we want to. We can do an A/B test of, you know, we're upgrading something new, we want to canary it, we want to make sure it works. We could upgrade something, check that it works, maybe it doesn't, we roll it back, but we haven't created a blast radius of that, right? We've diminished the blast radius just down to something like a single peering session. Likewise, maybe we connect in a large IX, and you might have 1,000 peers on that. Right? That poor router having to do 1,000 peers and dealing with an ARP of 1,000 devices and things like that. Again, we kind of have this flexibility that we can shard these out however we want, we can plane them out however we want, and you know, scale it however we want. Getting back to the slide title, right? No packet left behind. We want convergence to be as fast as possible. We want to have the highest availability possible, and that's kind of what was driving decisions of how we then run the control plane of these. It still has to be BGP because that's the protocol that the internet works on, right? But just because you announce something to us doesn't mean that we actually use it. We might probe it first to see that it actually is real, that you announcing a prefix to us, that you do actually have reachability to that. We can run RPKI separate from this on something that is much more performant, right? So you can kind of see this in a few ways, and for those of you that do peer with us, and I picked actually, I logged on a router actually in Brisbane. This is Aussie Broadband at the bottom there is one of their sessions to it, but I removed the IP addresses so you can't see, you can't ping this yourself. But the top one here is some random peer. We get these questions from peers every now and again. If you ping us from the connected device that you're on, you actually get 2 responses back. What's up with that? And you know, you can see this here, right? You get the first one, then you get a dupe response with a different TTL. We kind of left this in just from debugging originally. One is coming from the physical device itself, and one is coming from the container running the BGP stack. And so we initially had this when we were first deploying this thing, just to validate that we had all of our tunnels and things set up correctly to make this thing work, and we could troubleshoot based on that, but we actually left it in. We just didn't take it out. But it's only the directly attached peer will see this. You have to use the connected /31 address or whatever. It's the only one that gets that sort of special treatment and can see it. The other way that you can see it, if you are attached to this new thing, is we're all big fans of Melbourne AC/DC. We didn't have an AC/DC MAC address, but we had a MAC address that was really close to it inside Amazon. So it's A0D0DC is the vendor OUI of all of these devices. Just call that my little quirks. You get little enjoyment in life in doing little geeky things. So every device has that MAC address. Now, as we kind of progressed along, there was sort of all sorts of learnings from doing this and unexpected things. One of the things that we learned is I think we're kind of the first for doing some of this behavior. And the reason we found this is for IPv6 neighbor solicitation, there's sort of some interesting quirks in what IP addresses are chosen between link local and unicast addresses of what you've actually put on the link itself. This was actually, I think, a session we had going to TPG was where we first hit this one. Actually, sorry, no, this wasn't TPG, but I've forgotten who this is. But anyway, we'd hit this quirk in Linux where the default for Linux is for doing neighbor solicitation is it will choose the source address of the link local address, FE80, sending at the unicast of the neighbor. That's its default behavior. And many people ACL this out. They don't think about link local. You know, it's kind of eternally frustrating, some of the choices that folks made when they standardized IPv6. Some of these things might have been good ideas at the time, but it's amazing how many people actually misconfigure these things, right? And this is a good example of we had a neighbor that we would try to do neighbor solicitation. In our case, we set it to retry 36 times, and it would not answer 36 times. And then, and it would fail. And then we'd have to, it would be aged out, and there would be a traffic disruption as a result of that, and it had to be relearned, and away we go again. We found in Linux there was this setting called mcast resolicit, and you can change this flag, and then what it does is Linux will flip to use FE80 on both the source and the destination after it's failed the initial attempts. And then we kind of found this was the way of making this work reliably everywhere. I don't think this is a documented behavior. I assume that Juniper, Cisco, Arista, everyone else has found this out the hard way, but it never got documented anywhere, right? And it's up to us to rediscover this little quirk of V6. And you know, we kind of ended up with this little pattern of, you know, we could debug it, right? We can run TCP dump on our devices. We could run sort of standard Linux commands. IP monitor the neighbor table, right? These are all just standard Linuxy things, allow you to see the netlink messages. And we figured it out, right? But it was kind of like a great example of like, well, actually the Linux defaults aren't very good, number one, and number two, clearly people put wrong ACLs for V6 still these days, right? That was one of the ones that was kind of interesting discovery. Another discovery we had along the way as well was this one, and it was Cisco's handling of link local V6 next hops. This was actually a combination of, I guess, a bug on our side and a bug on their side. At the top is a BGP route update that we sent going out, and the bug, I guess, in this is we were indicating both a unicast next hop and a link local next hop. And in fact, what we were indicating here with the link local FE80 next hop was the link local of the container in Linux where the BGP stack was running. Well, that ain't attached in any way, shape, or form to where the BGP session is. Now, what you would expect, so that was a bug on our side, and we fixed that. But what we would expect is for the neighbor, it would see the it would see that one of the addresses is fully resolved and one is not, and it would use the one that is fully resolved. Well, it turns out that Cisco has some logic in, I think it's classic, I think it's iOS XE specifically, so classic iOS, where if it sees a link local one, it will just keep trying to use that, regardless of if it has the other one fully resolved. And kind of how this manifested itself was V6 didn't work. was the short answer, right? So again, we kind of had to work around that. We figured it out. We could do that. It was easy enough to do. But it kind of, again, highlighted some of the traps for maybe for doing, in our case, this off-box BGP thing. It was unintended that we were picking up the link local in the update messages. We didn't intend to do that, but you know, hey, it was a software bug and easy for humans to overlook. We had peering at this point at thousands of sessions before we hit this. And I think all it took was someone running iOS XE for us to hit it, right? So, and we can kind of see that here, right? So, those are kind of some of the challenges that we've had along the way, right? But like, kind of what has been cool about this is, you know, back to the size of the network, we're deployed at this in hundreds of locations around the world. It is how we've actually scaled all capacity for about the last 3 years. For many of you, you're peering on it and probably don't even realize, right? Because it doesn't show up any different. But we have kind of fundamentally changed this entire network, and we did this during COVID, and we had to do it this way because we had to scale the network in such a huge, huge way. Everyone wanted their Zoom calls and things to work. You know, we were a certain degree of successful at doing that. What would be cool, I'm just sort of finishing up here, is for those of you that do connect to us, we want to be really, really well connected to you, right? We are in most capital cities where we have peering. Please make sure that you connect to us well. You should be sub 2 millisecond connectivity to the IPs that we have listed. If they're not, come talk to us, right? We should be able to fix this up. You can go to this URL. I think the slides will be available, and you could even confirm where we think you're coming in from an Anycast perspective, right? And sort of a shout out here, right, is if you do want to peer with us, just talk to us, right? We're pretty friendly. We've got a bunch of friendly people. Jocelyn and team, yep, are all friendly folks. You can even self-service doing peering with us. Interconnect.amazon is a peering portal. You can, we actually automate most of the process for peering with us. For those of you here, we'd even love to peer with you in any location you are in. The perfect world would be that, you know, if you do have a network across the Pacific, if you're on the west coast of the US, we'd love to connect to you there as well. If you're on the east coast of the US, we'd love to connect to you there as well, right? It's often misunderstood how we route globally between regions, but the more connectivity we have, the better it is, right? So, and sort of with finishing up, this isn't my cartoon, I guess. This was Randall that put this together as an XKCD, but it's pretty accurate. We had no involvement in this. I just asked him if I could use it, and he said yes. But it's we kind of ignore parts of the OSI stack in how we do things in the network, right? It's we do kind of do things at L1 through L7, and it's this Jenga thing that we have in how this fits together. We're not the only ones, right? I think Jeff alluded to, like, all of the big guys are doing interesting things, right? And Tom's talk as well on, you know, a big part of it is DNS as well, right? Yeah, we're all a pretty friendly bunch. We're pretty proud of what we've been able to do, and yeah, we're more than happy to connect with all of you guys. With that, I'm happy to take any questions.